So, hello.
Hello, sir.
Yeah,
Hello, sir.
sorry for the late. Actually, my pen was not working, so that is why. Let's see what is happening. Okay, okay. So I have finished my last lecture with the definition of local homeomorphism. Local homeomorphism between what does it mean by a local homeomorphism? That is a continuous map from a space E to B is said to be a local homeomorphism if each point of each point of the space E uh, each point of the space E is okay, has a neighborhood, yes, has a neighborhood which is homeomorphic to an open set in B. Yes. P E to B is said to be a local homeomorphism if each point of the space E has a neighborhood which is homeomorphic to an open set in B. So, as an example, I have already told you that the map from R plus to S1 defined by this is a local homeomorphism, but it fails to be a covering map. Covering, fine. Okay. So later we will see that there is a connection between a local homeomorphism and a covering map also. That is a covering map. Yes, a covering map is always a local homeomorphism. Is always a local homeomorphism, but the converse is not true, as it is clear from the above example. The converse is not true. Yes, converse is not true in general. Fine. Now we will talk of the converse a bit later, that a local homeomorphism will be a covering map, but it satisfies some property. So there is a property which will help you to show that a local homeomorphism will be a covering map between two spaces having some topological property. And you will see that the spaces we are concerned will be locally path connected, locally simply connected and connected. So these things will be will uh, have a have an important role in this discussion. Yes, fine. Okay, so let me give you another example. Uh, that is, one may think that for S1, R is the only connected covering space. But this is not the case, because that example that R is not the only connected covering space. Of the circle S1. As you see that the map defined by this, by the rule Ez equals to Z square, Z square, yes, this one. So this will be a covering map. This is a covering map. Okay, why? Just I will give you a sketch of this proof just by that. If you if you consider one open set here, this one. So if we consider this open set, just for an example, the case for the other ones are quite similar. So actually, so this set is actually looks like this form. So it is, yes. So then what will happen? So we will take this one. So this will be pi by 4. So each Vn, so this U will have the property that suppose Vn is the set of all those complex numbers satisfying this problem, this condition. And this is true. Okay. I think, yeah. Okay. So I don't need to write this. Yes. Yes. Okay. So then V will be so this is the set. Yes. Right. And so P inverse U will have, I think, yes. So here will be two sets. Yes. Yeah. So this one and this one, yes. So it is V1, V2. Right. And each of these VI's, this is a homeomorphism by the same arguments as we have encountered in the example of the covering map P from R to S1. Yeah. So this tells us that. So yes, fine. So with the help of this picture, you can see that this S1 is itself a covering space of S1 with the help of this P. Fine. Another fact is that P be a covering map and if suppose B dashed subset of B and E dashed equals to the P inverse E, then the map, the restriction over E dash to B dashed, this will again be a covering.
You mean E prime is equal to P inverse of B prime, right?
Right. Sorry. Yes. Thank you. B prime. So this is again a covering map. Although we have seen that the restriction map of a covering map did not be a covering map, as we have seen in the example of P from R plus to S1. Okay, fine. So why it is true? Because if you take any point from B dashed, then it will have a neighborhood U. Suppose you have a point this, then definitely there exists a neighborhood U of B dashed in the space B, such that it can be represented as the decomposition of V alphas, where V alphas are disjoint open sets. And then you take the intersection, that is U intersection B dashed. So this will be a neighborhood of B dashed in capital B dashed. And the sets V alpha intersection E dashed will give you the required decomposition into slices. That is P inverse of U intersection B dashed will be V alpha intersection E dashed. So these are very easy to see, and you can check that each V alpha intersection E dashed is homeomorphic with U intersection B dashed. So this can be so left as an exercise. The last part. Yeah. And another important fact which will be used later, that if you consider two covering maps, one is from E to B and another one from P star colon E star to B star. Yeah. So if these are two covering maps, then the product map, that is this from this to this. So the definition is it will be yes. So this will again be a covering map. So this is very easy to see, because if you just use the definition of these two maps and by simple set theoretic properties. So this will be left as an exercise. Yeah. Okay. So with the help of this result, you will see that since P R2S1 was a covering map, then definitely the product map P cross P this is a covering map. And we will see that this space, maybe in my next lecture I will give you the explanation of this one, that this S1 cross S1 is actually homeomorphic to the torus. That actually Somo already talked about this surface already. Yes, this one. Yeah, fine. And this map will be used to compute the fundamental group of the torus. Right. So now I move to the property that I have already told you, that the property which makes a local homeomorphism into a covering map. So what is that? So let me introduce the notion of lifting of a continuous map. So what does it mean? The definition is like that suppose you have a map from this. Suppose P be a map from E to B, and F be a continuous map from a space X into B. Then a lifting of F is defined to be a map F tilde from X to E, satisfying P compose F tilde equals to F. So this map is called a lifting of the continuous map F from X to B. So it is a lifting of F to B to E. Yes. And we shall investigate the existence of liftings in covering spaces. And that will be more interesting. and which will help us to characterize the fundamental groups of different spaces. Because I have already informed you that basically there are two ways to compute these fundamental groups. That one you will just doing by covering spaces, and then you choose the deformation retraction. Okay. So for a covering space, we see that paths can be lifted. And not only that, not only paths, you will see that path homotopies can be lifted as well. So let us have a look at some examples of liftings. That is, basically I will concentrate on the map, this one. That is P T is e to the power this one. So that is, if we draw the pictures, then you will see that suppose someone is saying that, sir, please send previous and these lecture notes. Let me finish first. Okay. Okay. So this is a real line. So this is the interval 0, 1. So let F be the map which is the upper semicircle, this one. So this is a path from this point to this point. Okay. And P be the map from R to S1. Yes. So then you will see that this F has a lifting to R. What is that lifting? That is, if you take, this is 0, this is 1, this is half, and this is 1. Yeah. Then you will see that this one is a lifting. That is the path from 0 to half defined by, so F tilde T is half of T. So this F lifts to this path, F tilde, which starts at 0 and ends at half. And similarly, you can take another example of lifting here. So if you take again the real line R, and suppose this is the circle, and let us take the lower semicircle. Yes. So that is 0 to 1. So this is your G. So then half, this is 1, this is minus half, this is minus 1. So then you will see that, so the path from 0 to minus half, so this is a lifting to the path G. That means, so this will be, so this is actually minus half t. Fine. And again, you can check another one. So let us have a look at another one.
Abhishek, yeah,
Yeah.
I think you should mention that this lift is not unique, right? So there are actually
Yes.
infinitely many lifts of the same path. Namely, if you choose the starting
Yes.
point,
Yes. Yes. Right. Okay. So you want to tell me that I shall I give you another examples of paths, liftings, right?
no, I'm saying this. That's given such an f,
Yes.
this f tilde is not unique.
No, no, no.
So f
Definitely.
tilde,
Definitely. Yes.
yeah,
Now,
you could have very well started. If you fix,
yes.
if you fix the starting point, then there is this
Mm-hmm.
path, this 0 to half path is unique. But
Mm-hmm.
say if you, if you you can also lift
Oh,
this to a path that starts at -1 to -half, right? That is also another lift.
okay. Which one?
Again, for, so yeah, you take -1 here on the real line
Okay.
in the same picture, yes,
Mhm.
and
Okay.
you take -half.
Okay. Fine.
Okay, then you take the path from -1 to -half.
Fine.
Basically, you are taking f tilde t equal to
Hmm.
half t minus 1, this
Yes.
function,
Right. Okay.
half of t minus 1.
Half.
So
Yes. Yes.
that will be another lift of the same f, and same for
Yes.
any other integer. So you can start with any integer n, and from
Yes.
n
Yes.
to
Because
n
the
plus half.
function is periodic. So since the function is periodic, so that is the property, right? I think.
Right, right. So because every point below on the circle has infinitely many lifts on the r.
Hmm.
So any such path on a circle
Mm-hmm.
will be lifting to infinitely
Definitely.
many paths above.
Surely.
But once you
Then it
fix
is.
one
Then
of
it
the
is.
points
Then it is.
that,
Then it is unique. Yes. That is the theorem.
yes, yeah,
Once you fix it, then it is unique. Certainly.
yeah, so one point you have to fix like 0 or -1,
Hmm.
then this is unique.
Yes. Surely. Yes. Fine. Yes. Okay. Okay. So you can take another path also. You can take a H which wraps the uh, uh, circle twice. So then you will get another. Then you will find one lifting also. So actually, you can. These are very easy things. So, but okay, fine. Okay. Yes. So now I need to record one lemma here, which is like that if you consider one local homeomorphism and suppose uh, suppose f is a continuous map from x to b. And the condition is that if f1, f2 be two liftings of f, such that for some x0, these two liftings, actually I should write this, yes, will agree at this point. Okay. Now if you consider x to be a space, a connected Hausdorff space, then you will see that these two are same. Yeah. If they agree at a point, and if the space x is connected T2, then you will see that these two lifts are same. So this can be okay. Actually, you can do this by just, I will give you one thing, that you just take just define the set x naught equal to set of all those x, so that these two maps agree. And these are the this is the common technique to show this fact by the help of connectedness, that you will show that this x naught is it is actually a non-empty set. So you need to check whether it is both closed and open, and then you will get that x naught is actually x. So this will be left as an exercise. Yeah. Fine. Now I want to define one thing, that okay, let P from suppose we consider a local homeomorphism. Okay, fine. Local homeomorphism. Then P is said to have path lifting property if for a point E naught belongs to capital E and alpha be a path in B which starts at which satisfies satisfies alpha of 0 will be P naught. Suppose you may denote this by B naught. Yeah. Then there exists a lift this from the closed interval 0, 1 to E of alpha such that this alpha tilde starts at E naught. That is, if you draw the picture, then you will see that. So suppose it is B and it is E. So you have a map from this, and it is E naught, and it will go to B naught. And if you consider a path alpha starts at B naught, then it will have a lifting here which starts at E naught. Yes, this is alpha tilde. This is alpha. That is so okay. So P compose this is alpha. Yes, fine. Then I can give you a result with this fact, which is required to be continuous, Gunjit. A path is a continuous map always, yes. Okay, so the result is that let P be a local homeomorphism having path lifting property. Yes, path lifting property. And suppose that E is path connected and B is simply connected. Then obviously P is a homeomorphism. So then P is a homeomorphism. Why it is true? So it remains to check the oneness and ontoness of this map. Since it is a local homeomorphism, so you can show that this is an open map. It is continuous. So it remains to check that whether it is 1 1 or 1 1 and onto or not. So it is obviously true that this P is onto. Why it is true? Just because of the definition. Because just okay. So if you take this is B, this is your E. So Yeah. So let this is, let us fix E naught, and okay, so it will go to B naught. Yes. Then let B be any point of capital B, that is here. So you have a path from B naught to B. This is alpha. Since B is simply connected, so in particular it is path connected. So you can always have a path from B naught to B. So then with the help of lifting property, you can lift this path to alpha tilde. And this alpha tilde will start at E naught. Then P of this, where it ends. So let us take the value of P at alpha tilde 1. So then it will be P compose alpha tilde of 1. So this is alpha. And what is alpha 1? Alpha 1 is B. So therefore, this P is onto. Gunjit is saying that, what is the problem, Gunjit? The function that I wrote doesn't seem to be continuous in standard topology now. Which one?
Sir, in the lifting of F examples that you gave,
Which example?
in the first example of lifting,
Lifting. First example. Which one? This one.
sir, it is above. From 0, 1 to R, you said na, the lift is, uh, yes, sir, you can take this G1 also, G also.
This one.
Yeah, so here, sir, G tilde, is it continuous function?
It is not continuous. You are saying that.
Yes, sir. So how are you
Right.
like defining
This is your
this?
exercise. Check G tilde is continuous.
Okay, sir.
Just forget those liftings and check whether G tilde is continuous. So it is defined by this. This is a very basic thing. This is so.
Okay, sir.
Okay, fine. So now it remains to check the oneness. So P is 1, 1. So why it is true? So suppose you have so again, so this is E, sorry, this is B and this is E. This is your P. And take uh, 2 points, E naught and E1. And then you have a path, since E is path connected. Write it as alpha tilde. Okay. So then, suppose that P E naught equal to P E1. Suppose let us denote this by B. Okay, this. So E naught and this will go to the same point. This is B. Okay. So then what is P compose alpha tilde? So what is this? So this is actually, so P compose, so let us take this as alpha, then this will be a loop. This is a loop in B based at B. So this is a loop in B based at B, and now since B is simply connected, so this alpha is homotopic to a constant path, which is B bar. And you will find out, you can find out one homotopy H to B such that this is alpha H of, and this is B. And not only that, on the left and right sides of the unit square, it will be B. So that is, you are actually getting a family of functions Ht from 0, 1 to B such that whose 0th function is alpha and 1th function is the constant map B. And also at point 0 and 1 they agrees, right? Okay. Now these HTs, since they are continuous map from 0, 1 to B, so actually they are paths. So these HTs has liftings. So suppose their lifting is denoted by lift of HT. This one. With the property that these lifts will start from, so since HT0 is B, so what is B? B is P naught. So it will start from E naught. So this is E naught. And the first lifting will be alpha tilde. Okay. Then with the help of okay, I'll prove this theorem later, that so these liftings, so T goes to this, this is a constant. That is, these HT tildes will end at the same point. So that means, so where it will end, it will end where alpha tilde ends, that is E1. Now since H1 is the map this, the constant map B, yes, so therefore its lifting is a constant loop, right? So therefore this one equals to this one. Now what is H1 cap 0? This is E0 and this is E1. So this proves that P is 1, 1. So it remains to check this one. I will show it later. Okay. So by assuming this one, I can prove this. This P is 1, 1. Okay. So now let us come to this corollary, which is, suppose P be a local homeomorphism P be a local homeomorphism with P of E is B, and let us take E is locally path connected and B is locally simply connected. Then P is a covering map if and only if P admits path lifting property. So how could you show that? Very simple. I have already, so I'm just going to give you the sketch. So suppose you take one point from the space B, B, capital B. Now since B is locally simply connected, then you will get a simply connected neighborhood. So there exists a simply connected neighborhood U of B0 in B. Okay. Now since P is continuous, so definitely P inverse U, I may take it, okay, open neighborhood, yes, fine. Then P inverse U is open in E. And since E is locally path connected, then you can decompose this P inverse U into union of V alphas, where V alphas are disjoint open connected sets. Open connected sets. Okay. Now you use the property that P has Okay. So let P has path lifting property. Then what will happen? Then its restriction, that is P restricted to V alpha to U. So this map will also admit path lifting property. Why? As because if you choose one point from V alpha, just take one E and E from V alpha and take one path from I to U. So be a path satisfying this path starts at P, and then you can have a lift, so lift of alpha. Then alpha tilde 0, so it will start at E. Okay, now E belongs to VL. Then by the use of connectedness, and since V alphas are all disjoint, so this will remain fully on V alpha. So this shows that this P restricted to V alpha has path lifting property. So then this map so this map has the property of this result. Yes. So here V alpha is path connected. Yes. So these V alphas are path connected and U is simply connected. And V restricted to V alpha has path lifting property. So you will definitely have that this map is a homeomorphism. Yeah. Okay. Fine. Actually, sorry. For the only part, yes, okay. Sorry. The only part, yes. Just prove this lemma. What is that? This will be this case will be the particular one then, because if you just prove this one, that is taking any covering map, be a covering map, and suppose you fix a point, what Somo says, that fix a point E naught, P naught is equal to B naught, then any path alpha from this which starts at B naught, it has a unique lifting alpha tilde in E which starts at E naught. So how to prove this one? So certainly again we are using the connectedness and the definition of covering map. So since P is a covering map, so let us it will be better to visualize that this is your E. So you need to just take one E naught and then place it here. This is your P. And if you take one path from starts at B naught, then you will definitely have a lifting of this path to E which starts at this. And this lifting is unique. Yes. So what is the sketch of the proof? Just take, okay, now since P is a covering map, so then one can cover the space B by an open covering U alpha, in which every U alphas is evenly covered by P. Why? Because why it is true? Since just by using the definition of covering map, right? That is, this B will be the union of U alphas, where each U alpha are evenly covered by P. Okay. So then their inverse images, P inverse U alpha. So this will be actually union of slices, disjoint slices, so that you can denote it by, suppose it is V alpha B. Yes. So these are disjoint slices. That is, this is homeomorphic with U alphas by P, restriction of P to this. Now then for each S belongs to the closed interval 0, 1. Then what is alpha S? What it will do? So this alpha S will be in B. This one. This is S. So this alpha S is in B. But B is covered by this UV. So that means this S is the union of alpha inverse UV. Okay. Yes. Now, now since alpha inverse of UV is open in 0, 1, so there exists an open interval, and more specifically you will get one closed interval, right? Interval. Suppose S S dashed, S double dashed. Okay, fine. Such that S belongs to this, and this is a subset of F inverse of UVs, and this is this. So then what will happen? Then I is covered by union of this one, since each S is in some F inverse of UV, but I is compact, so you will get finitely many UVs. So that means, so that is, there exist S naught, S1, Sn in I, such that the first is 0 and the last one is 1, and you have the property that F of each subinterval is actually a subset of this. Okay, so then, so you need to construct this sorry, this is alpha, sorry. Yeah. These are alpha. Yeah. So you need to construct, so our aim is to construct this lifting alpha tilde. So okay, so what is the construction? Now let alpha of S naught S1, so it is a subset of, suppose we denote this by U naught. Okay, then what will happen? Then consider the point which is P inverse of alpha of S naught. What is that? What is alpha is not? S naught is 0, so it is alpha 0. And what is alpha 0? It is B naught. Now, sorry, this is P inverse of B naught, yes. So this set, so this will spread across the disjoint open sets, which are V alpha knots, because as you have seen that P inverse of U naught will be this. Since these are disjoint, so each, and I have already shown that this P inverse of B naught, these sets are discrete. That is, at each slice it will have exactly 1 point. So if I write down the, so let me, so the proof is a bit technical, but you need to understand what is what. This is Sn, and you have, this is B, and this is your B naught, and this is your U. Yes. So this B naught is alpha naught. That is, alpha is naught. So then here we have just two slices of this one. So this, so inverse will have 1 point here, 1 point here. So each slice will have 1 point. Suppose this is your V naught. This one is your V alpha naught. Okay. So then, so this is your alpha. So you need to construct one alpha tilde. Okay. So then, now since, so how to define this one first? So now recall that now P of E naught is B naught, and what is B naught? B naught is alpha naught, that is alpha is naught. So that means E naught is in, that is P inverse of alpha is naught. I need to denote like this to since the slice, so this E naught is contained in some slice. Suppose this is your okay, V alpha naught. Yes, fine. This is your E naught. Yes, fine. So we define f cap of S naught is equal to E naught. That is your sorry, this is alpha. Yes. So alpha tilde of S naught is E naught. That is the, we are constructing the lift which starts at E naught. We need to establish this fact. So facts to be established. What is that? That is, if alpha is P compose of alpha tilde. Now how it is true? Because alpha tilde of this subinterval, so this is actually this is a subset of P inverse of alpha of this one. And this is a subset of P inverse of U naught. And alpha tilde of S naught is E naught. Where E naught lies? E naught lies on V alpha naught. So then, by using the connectedness and the disjoint property of V alphas, you can say that alpha of this is this by assuming continuity. The continuity of this one, right? So the definition is that, so we need to establish the continuity of alpha tilde by defining alpha tilde on the subinterval S0 to S1, and the other case will follow like this. That is, we define alpha tilde of S is equal to the inverse of the restriction map of this of alpha S for each S belongs to this one. This one. Now, since this map is a homeomorphism, so this map is a homeomorphism of V alpha naught onto U naught. And so this map is well defined. This map is well defined. And the if this alpha cap is actually, so P restricted to V alpha naught of compose alpha tilde, yes. So this will be the alpha over alpha naught S naught S1, yes. So alpha tilde will be P restricted to V alpha naught inverse compose alpha over the closed interval this. So being a composition of two continuous maps, so it is a continuous map. Okay. So after defining this function on S0 to S1, you can proceed to the other interval, the next one, that is S1 to S2. And then by the use of induction, you can actually cover up all the subintervals, since the number of subintervals is finite. Okay. So in this way, you can have a function alpha tilde from the closed interval 0, 1 to E, which is a continuous map, and P compose of alpha tilde will be alpha. So I think you can do this on your own. So the rest part will be leave as an exercise. You can proceed as the above, just by using continuity and the connectedness property, and also by using the method of induction. And since we have specified this value, so with the help of the first lemma that I have already told you regarding the map, which is a local homeomorphism, and if you choose one connected T2 space, and which is our 0, 1 closed interval, this is a connected T2 space, so this alpha will not have two liftings because it will agree at one point. So therefore, it will agree on the whole of the interval. So this lifting will be unique. Okay, so now it is 5:46. So this is a bit technical, but I need to cover these details. Yes, because these are very important things. So I need to stop here because I will tell you so in the next lecture I will compute the fundamental group of S1. And also I can introduce the deformation retracts. Yes. Okay. Okay. So any queries or comments? Actually, I started late because my pen was not working. So that is why it takes more time. So Sumanto, shall I stop here?
Yes, sir. Yes, sir. There are no questions actually.
Okay. Somo, thanks for your comments. If you are here, I don't know. No, he is not here. Okay, fine.